Hello everyone, I'm Lee Xin-Yan. Today, I'm excited to share with you the latest work from a collaboration between Shanghai Jiaotong University and the NRIO lab named POEM, Reconstructing Hand in a Point Embedded Multi-View Stereo. Firstly, let me introduce the hand mesh reconstruction task. It plays a critical role in the field of augmented and mixed reality. It can enable users to interact with their environment. There are two groundbreaking methods in this field, the pose estimation of hand skeletons and the reconstruction of hand surface mesh models. These approaches have inspired numerous works in this field, with new findings coming out each year. The single-view mesh reconstruction problem remains challenging for practical applications for three primary reasons. First, depth ambiguity. Recovering the absolute position in a monocular camera system is an ill-posed problem. Second, uncertainty in camera projection. The focal length and principal point offset of the camera are unknown. Third, occlusion. If the hands interact with objects, occlusion poses a challenge for the accuracy of mesh reconstruction. These limitations of single-view hand reconstruction have restricted its application in AR because we require the hand's precise and absolute position in camera space. Given the challenges posed by single-view hand mesh reconstruction, we propose a multi-view approach as an alternative solution. This approach is motivated by two reasons. Firstly, the three issues can be addressed effectively through multi-view reconstruction. Secondly, recent developments in industry and academia, such as AR glasses and multi-camera motion capture platforms, have created a growing need for multi-view hand reconstruction techniques that can be applied directly to practical applications. In the early days, multi-view methods mainly focused on key points estimation, which means only the skeleton without surface. Their approach was a classic two-stage method. Firstly, they obtained the 2D positions of key points from the images. Then, by employing techniques such as triangulation to lift from 2D to 3D, they were able to obtain 3D skeleton information. One of the crucial challenges in multi-view tasks is how to effectively fuse features from different images into a unified space. This involves two steps. First, unifying the observations from multiple camera views into a common space, and, second, fusing features in this space. For the first step, we utilized the concept of position encoding. The core idea is to provide a unique identifier for each pixel, to distinguish their different positions for collective operations, such as self-attention. To unify multiple camera views into a common space, we assigned a position encoding to each pixel, representing its location in 3D space. With this in mind, position encoding is commonly divided into four forms, that are pixel form, line form, point form, and voxel form. It's worth noting that although all the position encoding methods encode 3D information, only the voxel operator can directly utilize this information. This is because neither 2D CNNs nor vision transformers can preserve 3D spatial information. Our goal is to find a method that can strike a balance between holistic feature representation and local property while leveraging 3D position encodings. Our method is called POEM, and its core is a multi-view stereo space embedded with points. Our inspiration for this came from the basis point set, which bases on a simple yet effective idea that a complex 3D shape can be represented by a fixed set of points, BPS, that wraps the shape in it. If we consider the intersection of different cameras' frustum spaces as a point cloud, and the hand's vertices as another point cloud, then the intersected space is the basis point set for hand vertices. This expression has two advantages. First, the hand is enveloped by a dense point cloud, which contains holistic multi-view features. Second, each point on the hand can selectively fuse features with points in its surrounding neighborhood, providing local properties. Here is the problem definition we use. Capital X to denote the 21 skeleton key points and capital V for the 778 hand surface mesh points. Our learning objective is to find a value for theta that maximizes the probability that X and V lie in the ground truth. Using the chain rule, we decompose the problem into two stages. In the first stage, we predict the key point X from the multi-view images using algebraic triangulation. In the second stage, we predict the hand mesh vertices based on X and the images. In our second stage, we embrace the idea of the basis point set, where the intersected camera frustum point set serves as the basis point set for hand vertices. Representing the camera frustum and hand vertices in point clouds has two advantages. First, point clouds are invariant to the permutation of points, only subject to the relative distance between points. Therefore, points from different camera frustums can easily fuse to the points in hand vertex point if they are spatially close. Second, point clouds are sets of 3D points with their coordinates serving as a natural positional encoding, making them suitable for the mechanism of attention. Once we have defined the modeling for the second stage, the problem becomes, how do we discretize the camera space into a space composed of point clouds? In other words, how do we embed 3D points into the camera space, and how do we embed image features into these 3D points? Lastly, how do we complete feature fusion between the 2 point clouds that are the camera space point cloud and the hand vertex point cloud? To embed points into camera frustum space, we discretize the camera's field of view into a mesh grid. Each cell in the grid stores the coordinates of a position point. Using the camera's external parameters, we are able to express in-camera mesh grid points in the same global coordinate system. Secondly, in order to embed image features into the 2 point clouds, we attempted 2 methods. The first method involved embedding each image feature into each 3D point within each mesh grid. This approach is similar to previous methods, such as 3D positional encoder and ray convolution. Next, we introduce the second method, where we extract features from the projected positions of the 3D mesh grid point across different cameras. We then use the Big G network to fuse these features, producing the feature that is embedded in each mesh grid point. In comparison to previous methods, projective aggregation is geometry aware. Here are 2 examples. First, 3D points that are restored from 2 different camera spaces can have almost the same features, as long as they are spatially close enough in 3D space. Second, 3D points restored from the same camera space can have very different 3D features if their 3D positions are far enough apart. Finally, we used the ball query approach to extract a subset of points surrounding the hand from the multi-view stereo. This subset of points served as the basis point set. Finally, with the 2 point clouds, one consisting of the camera frustum points and the other consisting of the hand mesh vertices, we designed a cross-set point attention mechanism to fuse features between the target set and the basis set. To predict the position of the hand vertex, we used an iteratively vertex update method whereby each decoder layer would only learn a delta based on the previous hand vertex position. We evaluated Polm's performance using 3 multi-view hand datasets, DEX-YCB, HO3D, and OKINC. All 3 datasets include dynamic interactions between the hand and object, where occlusion highlights the effectiveness of the multi-view approach. Our method outperformed other transformer-based methods, such as those using 3D position encoding, ray convolution, and feature transform layer, across all 3 datasets. Here we present some of our reconstruction results. For each multi-view frame, we display the result from 5 different views, with 1 view in normal size and the other 4 views displayed at half size. In conclusion, Polm addresses the issue of multi-view hand reconstruction using point representation. Our method operates directly on points through 2 novel designs, namely, point-based feature fusion and cross-set point attention. Moving forward, we hope to expand our research into general multi-view based object reconstruction, rendering, and animation. Thanks for your listening.